being for the problem. Okay? So if you want to go from rectangular coordinates to spherical coordinates, you are trading out x's for rho cosine theta sine phi, yes? And you're trading out y for rho sine theta sine phi. And z is equal to rho cosine phi. Right? Uh-oh. So this is a triple integral situation, yes? Right? Oh, well that means we're going to need a 3 by 3 permanent, yes? Eesh. So, we're going to have to be a little careful here. I'm not moving. I swear I'm not. So I'm just going to show you that it's going to be dx d rho, dx d theta, dx d phi on the top row, dy d rho in the middle, dy d theta, dy d phi. By the way, I know what you're thinking. You're thinking, does it matter which one goes on the top, middle, and back? Does it really matter if it's rho, phi, and theta? No, it doesn't. So, knock yourself out with that. It just looks stupid, I think, writing a certain way. I have these kids this year that every time I write a polynomial out of order, they just go nuts. In calculus, mind you. You'd think I divided by 0 or something horrible. You can't put x squared after x, Mr. Girl. That drives me nuts. Get over yourself. Okay? So, voila. Yes? We good? It's not bad, I promise. It really isn't bad. So let's chase this dog down and see what happens. So, first of all, the first column is totally easy. Let's get the win and get it over with, okay? Just drop the freaking rows, okay? For this whole first column, right? Let's get that out of the way. So, I'm going to start down here, and it's going to be cosine theta sine phi. It's going to be sine theta sine phi, and it's going to be cosine phi. That's that first column, and to me that was the easiest to get it out of the way. Yes?
Might be a side note. Is this also absolute values?
Yes. Well said. Nice. Now, let's do with respect to theta, shall we? So with respect to theta, the top one's going to end up being negative rho sine theta sine phi. The middle one is going to end up being rho cosine theta sine phi. And the bottom one's going to be a big fat 0. Because there is no theta. Alright? So everybody's a constant. Alright? Now, the x is going to be what? Well, it's going to be rho cosine theta, that part's all constant, cosine phi. It's going to be rho sine theta cosine phi, and it's going to be negative rho sine phi. Everyone good where I got that? Now we get to practice our determinants of 3 by 3s. Are we excited? Oh boy. Oh boy. I am. It's good times. Listen, this is one of those things that you should probably do every year just for good times. You should develop, I know what you think. You should sit down and, you should prove to yourself that, I don't know, let's see, well, quadratic formula, where it comes from every year. This is something you should probably chase through every year just for good times. No, probably not. So listen, so top row, this fella right here, normally we put I there, right? When we did cross products, but we're just going to use that value. So it's this guy times, now it's going to be this piece here times this piece here, yes? Yes? So it's going to be a negative rho squared cosine theta sine squared phi. Minus 0, of course, yes?
Well, wait, isn't there another sine theta in there?
It's sine times sine.
Oh,
So
it's multiplied by 0?
this times this, and then minus that times that, but that's 0.
Oh, okay.
Ah.
I thought we were, okay, so I thought we were can you draw the line?
No, that's going to confuse me. So, I'll kind of draw them and erase them. So there it is. Now, I'm going to take this middle fella, right? This guy right here, right? Right? Now, what happens when we're doing these cross products? When we do this 3 by 3 determinant, the middle one is always minus, right? But it's already minus, so plus. Rho sine theta sine phi. Now, who are we multiplying by? We're taking this guy here, this guy here, times this guy over here. So it's going to be negative rho sine theta sine squared phi. Nice. Oops. Minus, we're going to take who? This guy here times this guy here, right? So minus rho sine theta cosine squared phi. Nice. Plus, and I'll go down another line down if you don't mind. Plus who? Well, plus rho cosine theta cosine phi. And we're taking this guy times 0, so times 0 minus.
Well, why are we going that way all of a sudden?
It's not all of a sudden, that's how we do it. When you're on the far side, you take these two here.
Oh, really? Okay. I was gonna go.
Minus rho cosine theta sine phi cosine phi. That part looks goofy. Oh no, it's going to be okay. I see the problem. I see it now. I see it. We're good. I was like, no. All right. All right. All right. All right. So we're good there. It's not as bad as it looks. I swear. I swear. So let's distribute. Take this times this. So you're going to get negative rho squared cosine squared theta sine cubed phi plus, actually it's going to be minus, yes? Minus rho squared sine squared theta sine cubed phi minus rho squared sine squared theta sine phi cosine squared phi. Whew. How fun is this? Minus rho squared cosine squared theta cosine squared phi sine phi. Whew. Wow. All right, that's beautiful. What do you mean?
The center parentheses there, you have a sine squared cosine, or sine squared plus cosine squared distributed into negative sine theta, or negative cosine theta.
Yeah, interesting. Yeah, so you saw that right off the bat. Okay, if you saw this right off the bat, you could have pulled this business out, and you'd end up with a sine squared plus cosine squared. But if you didn't, it's going to come out in just a jiffy, I promise. I promise. Now, what down here on the bottom was everybody have in common?
Rho squared.
Well, let's take it out. Anything else they have in common?
Looks like a.
Negative.
Yeah, so hang on. So I'm going to take a negative rho squared out. Love it. I don't think they all have anything else in common. Okay? But we can probably group a couple of them together. Okay? So, like, who belongs with who? Maybe. Well, I see this fella and this guy belong together, don't they? Because they both have a sine cubed. You see that? So I think I'm going to put those two together. I think they're the ones that belong together, and I think these two over here belong together because they each have a sine phi tagging along, yes? Is that cool? So these two belong together. So they belong together, but what do they have in common? Well, they have this sine cubed in common, yes? If you will. So I'm going to pull that out of these two.
Sine theta, sine.
And so I end up with cosine squared theta plus sine squared theta, which of course is just 1. That's nice. Plus, now over here on these fellas, they each have a sine theta, a sine phi rather, in common. And that leaves me with a sine squared theta cosine squared theta plus, oh, sine squared, cosine squared phi, you dummy. Just a minute. Cosine squared phi, and then a cosine squared theta, and a cosine squared phi. Nice. There it is. Okay? And actually, what else could I have taken out? I could have also taken out a cosine squared phi out of those two as well, yes? So let's do that. Let me scoot that over a ways. Cosine squared phi, and it's sine squared plus cosine squared in there. Ah! Nice.
Are those thetas or the theta and a phi? Because sine squared plus cosine, that's just one.
Yeah, I know. That's why I did it. That's why I did it.
Oh,
That's the whole point.
okay, I see.
Nice.
So it's not just dumb luck,
No!
like their other problems.
No, none of this is dumb luck, man. All right, now. Yeah, square bracket. Now, I know what you're thinking. You're thinking, Jay, you screwed up. And every time I have to back away and stare at this for a minute. What does this and this have in common?
Sine phi.
I know. So let's take him out. And you're left with sine squared phi plus cosine squared phi, which of course is just 1. And so I'm left with this thing here. But this is supposed to be a Jacobian, ergo it really ought to be positive. And so when you go from dx, dy, dz's to spherical form, you will replace those with rho squared sine phi d rho d theta d phi in whatever particular order you want. But you must have the rho squared sine phi with you when you go. It is exactly like when we did r dr d theta. That's where it comes from. Whew. It's nasty. Okay? It's always, that always freaks me out every time I do that one off the cuff without preparing ahead of time, because I know a bunch of sine squares and cosine squares go away, but partway through every time I'm like, oh, you screwed it up. Every time I think that to myself. It drives me bananas. All right? Anyway, that is on page 885 in your text. They run through that again, not as in detail as I just did it, but they show how to get there. Yeah?
Is it any coincidence that rho happens to be in a three-dimensional circle versus r being in a one-dimensional circle?
Two-dimensional circle? Well, no, but that's how we defined it back in the day. Back in the first couple weeks we were here, we talked about spherical coordinate systems. R is a three-dimensional. It's the radius of a sphere.
No, I was talking about the squared versus the fact that a cylinder.
Oh, that's a good question. I didn't think about that. I don't know. It's a good
But
question.
if it has a phi squared, it's not a phi cubed,
No, it's good.
and yet it's still spherical.
Right, but the cylindrical
It was r dr d theta. Right. No, it's good. Here, just for fun, I'm not going to run through this one tonight. But if you were going from x, y's, and z's in cylindrical form, should we do it? We just take a jiffy. Yeah, what the heck? Here we go. Here we go. And we want to go to r's and thetas and z's. Well, first of all, are you expecting a change in z at all? No. If you were a betting man, what do you think the Jacobian here would be?
Or some theta, something, cosine theta,
r, dr, d theta.
or dr.
dz. Yeah, and R is the Jacobian there. It's just R. Because why? Because I just am changing the x's and y's, aren't I? So it's the same Jacobian as in polar form, because I didn't change my z's at all. Now you can show that pretty easily, because what is x in cylindrical form? Right? So the derivative of x so we'll just do with respect to r, with respect to theta, with respect to z, okay? Oops, and I write theta again. With respect to z, we'll do it in columns, okay? So of x, what's the derivative of x with respect to r? It's cosine theta. What's the derivative of y with respect to r? It's sine theta. What's the derivative of z with respect to r? 0. What's the derivative of x with respect to theta?
Negative.
Negative r sine theta. And r cosine theta. And the derivative of z with respect to theta is?
0.
0. And now what's the derivative of x with respect to z?
Nothing.
Right there. 0, 0, 1. Nice. So if you were to find the determinant of this beast, right, you're going to take the cosine, which is up there in the corner, the cosine of theta, times this guy times this guy minus 0, so it's going to be times r cosine theta, minus, and then it's going to be this top guy, so it's going to end up being plus then, right, because it's minus and minus, r sine theta, and it's going to be this guy times 1, so times sine theta, minus 0, of course, so nothing, and then plus, and then it's going to be 0 times, well, it's 0. Oh, that's handy. We literally did this 5 minutes ago. Well, probably 20 minutes ago. That last problem took a while. But that's definitely a win. Okay, so my Jacobian is r. Okay?
And so you take, what do you do with the Jacobian? So you take the r and put it.
So when you go from, so when you do dx, dy, dz, and you want to convert to cylindrical components, you replace x's with r cosine theta, y's with r sine theta, z's with z, and you replace this business with r, dr, d theta, dz in any particular order. But you must include the r, because that's your Jacobian.
So that's basically the multiplier.
Yeah, it's exactly like in U substitution when you do a du. It's exactly the same thing, except when you trade out multiple variables, they interact with each other differently. So that's why you have the extra piece there. Okay? In fact, it's kind of a cool thing.
Usually, if it comes to u and the v, you divide it. This time you multiply by the r.
It really comes down to what the values are. So in the case of cylindrical, it'll always be this. In the case of spherical, it'll always be rho squared sine phi. In any other one, it's going to depend on what you're using for let u equal this, let v equal this, or whatever equal this, right? So it depends. And you're going to have to chase it down on any particular problem. The most common ones are obviously polar form, where you go down that. Okay, so that's nice to see where it came from. Great. There's a spherical coordinate system. Why would I use a spherical triple integral as opposed to rectangular? Because it's bounded by a sphere. That's why. And it would be way easier than having a square root of a 9 minus x squared minus y squared, wouldn't it? Wouldn't it be easier just to convert that over to a spherical coordinate system? I think so, because it's spherical. If I was doing it in a cylindrical situation, not unlike the first problem we did today. As a matter of fact, well, one of the problems we did today, not the one I messed up, but the one we did in a cylinder that was extruded up like this, that would have been a very good candidate to use cylindrical components for. A very good one. Because if you had done that, it would make a lot of sense because your bounds, one of them was a cylinder. It would be kind of nice to do it in that regard. Not necessary, but nice. Okay? So that's what 12.8 is all about. So I'll do a couple of example problems like that from 12.8. But based on what you're bounded by, if you graph it like, geez, that's a sphere, then you should probably use spherical coordinates to make a substitution. Okay? Trade out your dx, dy, dz's for rho squared sine phi, dA, dρ, d rho, d theta, dt. Okay? I kept them the same letters. Anyway, but make those change out. Okay? Make those changes out and make it in a way that makes sense to you. Okay? So, I don't know, sometimes you have to make do with what you make do with. On the side of the road, look, I've got a pipe wrench. Okay, well, good luck changing the tire with that, but I guess you got to try something. Okay, it's not the best. It's really not the best, but you might make it work. Okay, I hope maybe. What's that?
Oh, recess.
Yeah. Anyway, you get the point. So you can sometimes do one a couple of different ways, but you're just sitting there going, God, I wish I had my impact wrench right now, or I'd settle for a tire iron right now, or a socket with an extension would be swell right about now. Anything but this freaking pipe wrench. Okay, but you know, sometimes it's one thing's better than
What
another.
about a hammer?
Completely useless. Thanks, Grandpa. That's what my grandpa would say. Yeah, this electrical thing isn't working. By God, get a bigger hammer. That's what we'd say back in the day. Yeah. Anywho, so that is 12.7, 12.9, and then 12.8. I'm just going to do a couple of examples more for the so you can see them. Okay. So 12.8 really is it does spend a lot of time dealing with, you know, here are the well, they say here are the Jacobians, now go to town. Well, once you understand the Jacobians, it's not very hard. So now I've showed you them, so then I'll just go and actually use them. Okay. So a couple more example problems. I will be sending out a review at some point this week with a key. It will be similar to the test. So help me God, if anybody says it's not exactly like the review, I will go 8 on you. It is a similar test. It is an older test. There it is. It's mostly chapter 12. But that's not to say that stuff from other chapters. For instance, like tonight we have to make an equation of a plane. We do a cross product tonight. We had to do a few of these things. So, and that's not to say I might ask you a question about a gradient or some such too, right? So, but it's not to say, but most of it will be chapter 12 stuff on the final. Most of it will be. Okay? There'll probably be one problem where I make you do it without a calculator. Like a double and a roll without a calculator. Oh my gosh, that's so hard. Maybe it's that problem. But the rest of it will just be here. Find this. Okay? And again, open notes, open books, because my tests are not, you can't Google that. Okay? Most of the problems are not that way. You actually have to figure it out. Here's what X and Y and Z's are bounded by. You can't type that into Google here and find that. Because the hard part is figuring out where the bounds go. Right? Any idiot can, by all means, use the calculator, use Wolf, use whatever to do the integrals, but the bounds is the tricky part. Okay? All right? That's all I got for tonight. I'll hang around and answer questions about the project if you want, for as long as you want. I'm going to go here first, and then, but yeah, then just hang out and we'll answer questions.
Can you just make a general note about like we're going to be presenting this and what's the expectation for the presentation part of it?
Yeah, so the expectation for the All right, so a little follow-up from last night. This is that first problem we did last night. If you recall, it was we did like 2 to 4, 0 to x, and 0 to 3 minus y minus x. I forget what the function was. Doesn't really matter right now. In this order. Here's the problem. This is the plane y equals x right here. Okay? So x equals 2, x equals 4. So obviously we need to be below this. So we're down into here, and we're between these two pieces here. We're above the purple plane, which is z equals 0. So we're in this region right in here. Okay? And then y equals x is this plane out here. Now notice it does not cut through in here where it should. Now I did not include y equals 0 because that's this plane that runs right across the front of this thing. It would cover up this little region in here. Okay? But it's that little region that we're interested in. Okay? That's what we're going to integrate over. But again, notice how this y equals x, and this is a problem that I made up, which is, or not, yeah, y equals, this is not y equals x. This is 3 minus y minus x. I'm sorry. This is y equals x. Anyway, notice how y equals x does not cut through this region in here. That's why we were not able to turn it inside out last night and solve it for the other one. For that to happen, we'd need a function to cut through like this. If it had cut through a plane like that, then we could pull this off. And so, let me demonstrate if I can for a minute. So over here, I graphed it, and I used an implicit surface for to do y equals x. So if I did y equals x minus 2 or something, see if I can pull one off that would just make it easier to go. See now how this piece, this light green cuts through there now? See, if that were true, then I could turn this function inside out, because notice how there's a little bit of a green plane right there. Follow it around right in there. See my little cursor floating around? There's a little bit of a green plane right in that region that we can then solve for, and that would give part of our integration there. But as it is, I can't do that. So, as a result, that problem I started last night was a mess. Couldn't do it. Alright? So I just want to clear that up. Now, a couple of examples tonight. Some problems in cylindrical and spherical format. And so here is one. It says, I want to take the integral of x over some volume, and E is the region we're going over, where E is bounded by z equals 0, z equals x plus y plus 5. The cylinders x squared plus y squared equal 4. And x squared plus y squared is 9. So again, because those two right there are cylinders forming part of our bounds, because of that, we are going to look at this in a cylindrical format. Okay? So again, looking at the x and y plane, in the x and y plane, of course, we could rewrite these as y equals in their square root function. However, it's bounded by that entire region, it looks like, at least anyways. So, that gives me this idea that, well, I've got a radius that goes from 2 to 3, and I've got a theta that looks like, at least at first blush anyway, looks like it goes 0 to 2 pi. Okay? We'll worry about that in a jiffy, but we'll see here. So, it looks like, to me anyway, my z is bounded above and below by those values. So if I were a betting man, that's where I'd jump in. I'd do that first. Okay? And then I've got this business here. Now, that to me is the way to go right off the bat. So some of you are thinking, well, wait a minute. If you're going to do dz first, which is totally fine, you can't have x's and y's up here. I know. I'm getting to it. It's okay. And then dr's and d thetas, okay? We'll worry about that in a minute. And of course, again, because it's cylindrical, we're going to have an r right there. Okay, so this bit just comes, again, r is the Jacobian for cylindrical terms. So again, the substitution that we're going to always use here is x equals r cosine theta and y equals r sine theta. So what we have then is r cosine theta plus r sine theta plus 5, 0. R cosine theta times r again, so really I have that. And I'm going to do dz, dr, d theta. And we get 2 to 3, 0, 2 pi. Okay. So let's try this. Pull up the calculator. Excuse me. Okay. So where are my r's and my x's? Okay, and the y's are thetas, and then I'm just do with respect to z from 0 to x cosine x times cosine y plus x times sine of y plus 5, comma, now with respect to x from 2 to 3, now with respect to y from 0 to 2 pi. (65 pi over 4). And that's the trick. Okay? So that's one way to do it. Of course, if you're going to do it in x's and y's, you'd have to split it. Either here and here. Okay? The problem is, it's going to be cut into 4 pieces, really. Either that or you just integrate. That's one way to do it. Or you could integrate the entire shooting match. So you could do it in a couple of ways if you're going to do this by Okay, so if I do this one, that'll give me the outer circle, and then if I subtract from that, this theoretically should work. Depends if I've been living right today, I suppose. Okay, and it should theoretically work. So I'll go ahead and try it on a calculator here. See what you think about it. Again, a person could do it pretty rapidly, but because we had cylindrical components, to me it just seemed the easiest and most obvious way to do it would be with respect to doing cylindrical coordinates. Oh, for Pete's sakes. Big dope. -2, comma 2. Okay, so I did the second one first. Interesting. Interesting. Oh. Big dummy. I see the problem. I went from 2 to 2, which that'll always work. There you go. Yeah, there we go. And then do the same thing again, but this time, of course, come back in here and change these 4s to 9s. So I just did them backwards. I should have done the ones with the 9s first. So minus ... 65 pi over 4. Oh baby, oh baby. Nice job, Jay. Had a kid. Thanks. Right. How about we try this one here? Yeah, here we go. Triple integral of. We're going from. Say we want to be bounded by. Where E is enclosed by the sphere. X squared plus y squared. E plus z squared equal 9, and we're in the first octant. Okay, so again, when we think about this here, okay, remember, phi, here's the z-axis, here's the xy plane down here. Phi is in here, yes? Because we're in the first octant, we're saying that phi is going to be pinched between 0 and 90 degrees, right? Or specifically pi over 2. And phi is or theta is also pinched between there and there, right? Because we're in the first octant. Now, what do I want to say? Right, and then r. Well, this is a radius of 3, so rho goes between 0 and 3. Okay, so that's a pretty easy one. Now, let's try it here and see what you think. So remember, when you're doing a triple integral in spherical coordinates, it's rho squared sine phi is the add-on that we need to use. We got x squared. Well, what is x? X is rho, so rho squared cosine theta squared, of course, and sine phi squared. So this really becomes then rho to the 4th cosine squared theta sine cubed of phi. Okay, and then notice how they're all independent of one another. So you can do them in any order you want to. So rho 0, 3, 0 pi over 2, 0 pi over 2, and we should be home free. And so let's see here, integrate, 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 and I guess I'll use p to the 4th times parentheses. Now don't forget when you do the cosine of theta, theta's over here. You can actually use theta if you like. you gotta do cosine squared like this times parentheses sine of, I'll use y cubed, comma p, comma 0, comma 3, comma theta, comma 0, comma pi divided by 2, comma y, comma 0, comma pi over 2, 81 pi over 10. Okay, now, could I have done it a different way? Sure, I could. If you think about it, my z is bounded by 9 minus x squared minus y squared. That's the upper part of the head. That's the upper hemisphere. So we're going from there up to there. Now our x. So let's think about this now. Here, looking down at our x and y coordinate, right? Down the xy plane, it's going to look like this. Yes, that is, when you looking from above, it's going to look like a circle with a radius of 3. So this is x squared plus y squared equal 9, which of course is y equals square root of 9 minus x squared. Right? So 0, y 9 minus x squared. And then of course this goes 0 to 3 because we're in the first quadrant. So we're going dz, dy, dx. Alright, so let's try this one. Again, the answer should be the same because it's the exact same region. Notice that back in the day, this was messier on account of, with your pushing the pencil around, you got all those dumb square roots and everything. That's why it was such a bigger deal back in the day to do some of these cute little tricks, because it really cleaned the thing up for us. Bugger. Sine of infinity. The heck's going on there, bro? No. And no. So, I think what happened when you do that situation sometimes is sometimes you end up with a situation where the calculator really doesn't know what to do with that. Yeah. So, I ran into a situation like that today where the computer algebra system gave the goofiest answer I'd ever seen in my life, where if you'd have just done it with a regular pencil and paper, you would have gotten this nice, easy, perfect answer, but the computer algebra system biffed it just a skosh. I think what you need to do maybe is be careful on is, yeah, I can't even see where I made a mistake. I didn't make a mistake. You can clearly see it's 81 pi over 10, but this sine of infinity bit's bugging me just a skosh. It's bugging me just a little bit, so I have to think about what that's about. But this is why we do it, is so much nicer, okay? If you were doing this by hand, well, you could take and look at, you could look at doing some substitutions and some trig substitutions and trig identities and stuff, and like you could look at this as sine of theta, of phi rather, cubed, and then, so if you're going to, see, if I want to integrate with respect to rho, any idiot can do that. If I want to integrate with respect to theta, or cosine squared, I have to rearrange that and do a double angle identity and stuff, and you can do that. And then of course sine cubed can be written as sine times a double angle, and then you can bust it out. And it's not horrible, it's not something I really want to do, but that's how easy it is to do these problems when you have spherical coordinate systems. Okay? Yeah, here, I think we'll do one more and we'll call it a day. So, yeah, here we go. So suppose you had the following integral. Negative 2 to 2. Negative square root of 4 minus y squared, square root of 4 minus y squared. And then, of course, x squared plus y squared. And 2. And xz. Now, before we go any further, what order do they go in? Well, this is what right here? Well, there's just no z's in it, so that's obviously a dz. The next one has y, so that's obviously x, and the last one, of course, is dy. Okay. Now, if you think about this, what is x squared plus y squared? Square root of x squared plus y squared. That's if you had z equals that. You know, if you had that down, obviously it's going to look somewhat cylindrical. That's a circle. This together all forms part of a circle. So if you had this set up the way it would be, it would look something like this. So let's go to the 3D calc plotter, and let's type in square root and of course you get z equals 0 as well. So on everything from there up to there. Okay, and x squared plus y squared is a cone, but it does have that circular look to it. Okay, and so then if you look down here on the xy plane, down here on this plane z equals 0, we're going to draw a circle on it basically. Okay, so what we have, when we look at that, come back in here, yes, we can start making some swaps out. So for instance, keep in mind x is equal to r cosine theta and y equals r sine theta. Well, let's start making our switches around here. Okay, oops, right, and of course z is just z. Okay, this is going to be an r cosine theta times z, of course. Okay, and because we're going to polar, we're going to have another r, so I'm going to put that as r squared. Cylindrical, I'm sorry, I said polar, I meant that. Okay, this is going to stay our z-axis, so what are you going to get? You're going to get the square root of r squared cosine squared plus r squared sine squared, which of course it's cosine squared plus sine squared is 1, so it's r squared, so square root of r squared, of course, is just r. So I'm going to go from r to 2. So this is dz, and then I'm going to probably go, I think, dr. So let's think about this. Here's the x and y plane. Here's that positive, oops. This is the top bound here. This is the other bound here. And then our x's go from here, our y's rather go from down here to up to here. You can do it any way you want to, but that's a radius of 2 with a theta 0, 2 pi, and oops, get carried away there. 0, 2 pi, and 0 to 2 for the radius. Okay, let me pause you for just a moment. Anyway, so it's a circle down here with the radius of that, so we're ready to take the integral. So I will do it both ways. Again, the data, it should work out both ways just fine. If it doesn't, you know, you screwed up. That's half the battle, is knowing you screwed up. So I'm going to do x times z. Don't forget to do that. You will be sorry if you do that. Interesting. Interesting. Uh-huh. 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 Okay, let's try this. So, down here, I'm going to try it again. Now remember, sometimes a person looks at that picture and goes, there's volume in that picture. Well, of course, you're integrating over a volume, right? So, of course, there's going to be volume there, but it's not the same volume as you're thinking of, right? So you're integrating over that volume, but you want to know what the hypervolume in essence is, right? So it's not the same at all. So some people get confused by that. Don't freak out. Darn you. Yeah, baby. 0 it is. Nice. So there is a little follow-up for you from yesterday. If you have any questions on those, please give me a jingle. We'll do some more examples for you if you need them.